Again, this lectures cover the introduction to normal distributions. Our main objective is to interpret graphs of normal probability distributions. Also to find the areas under the standard normal curve. We start with the properties of a normal distributions. Here we see a normal distribution random variable is continuous. A continuous random variable is based on measurements, and it has an infinity number of possible values that can be represented by an interval on the number line. Now, example here will be hours spent study in a day, and it can be between 0 hours to 24 hours. So the time spent study can be any number between 0 to 24. And this is based on, again, measurements. So it's, again, a continuous random variable. Now, a normal distribution also is a continuous probability distributions. We discussed about discrete probability distributions such as binomial distributions. So a normal distribution is a continuous probability distributions. So here we say probability distributions of a continuous random variable. A normal distribution also is a continuous probability distribution for a random variable x. And the most important continuous probability distribution in statistics. One of the reasons will be a normal distribution normally can be applied to even in nature events, such as, let's say, a human being. Beginning, a baby is not that strong. Height is very low. As time goes on, by the middle age, to be very strong. As time goes on, by the old age, it will be very weak, almost as a baby. So we'll see the curve of a normal distribution, which is a bell-shaped curve, beginning very low, in the middle going high, then it starts to go down. So again, normal distribution is the most important continuous probability distributions in statistics. And we can see the shape here. So we can talk about this event as a strength of a person. When you were born as a baby, your strength is very low. As time goes on, you get stronger. By the age of 40, 30, very strong. Then going 40 down, you start to be more weaker by the time 80, 90. If you can live that long, you'll be more weak as a baby again. Now, probability of normal distribution also have the mean, median, mode, which are equal and at the center. Now, sometimes we may say we may have a normal distribution that is skewed to the left, which means the median is greater than the mean, or skewed to the right, the mean is greater than the median. When it's symmetric or symmetrical in the center, it means the mean, median, and mode values are equal. So the example of this shape here means the mean, median, mode are in the center, they are equal. Also, the normal curve, as we said, is a bell shape and it's a symmetric about the mean. Also, the total area under the curve is always equal to 1. As we all know, probability values are between 0 to 1. And also, the normal curve approaches but never touches the x-axis as it extends further and further away from the mean. So we can see at the left side, but it never touches the x-axis. Also, the same thing applies to the right side as it goes further away from the mean or the center. Now, between the mean minus 1 standard deviation and mean plus 1 standard deviation, in the center of the curve, as we can see the graph, the arrow, mean minus 1 and 1 standard deviation, and also mean plus 1 standard deviation. It's called the inflection point, because this is the point where the graph will be changing from upward to downward. So here we say the graph curves downward, and the curves always upward to the left of mean minus standard deviation, and to the right of mean plus standard deviation. The point at which the curve changes from curving upward to curving downward are called inflection points. Again, if you take calculus in derivative, we have this concept also when the curve is increasing, then at the point that it will change from increasing to decreasing, it's called an inflection point. Same concept. Now, we also talk about the means and standard deviation, the effect it has on the normal distribution curve. Now, a normal distribution curve can have any mean value. Also, it can have any positive standard deviation. Standard deviation always have to be a positive value. Now, let's look at the first graph, which is our A. We can see that the normal curve is wider, which means the standard deviation is bigger. So there's a wide dispersion of the data set, wide in the spread of the data set. And the mean is in the center. But when we look at the curve B, we can see that the curve is no more wider, but rather kind of shrink, smaller. This means the standard deviation is very small, 0.7. So comparing the standard deviation of 0.7 and 1.5, we can see that the distribution with standard deviation 1.5 is more spread. The data will be spread, so wider. And when the standard deviation is very close to 0, we'll see that the curve will be shrinking because the data are not widely spread. Now also, we have effect on the mean. When the mean value is smaller, the curve will move to the left side. When the mean value is greater, the curve will move to the right side. So those are the two things that, again, the mean and standard deviation can have on the normal distribution curve. So here we say the mean gives the location of a line of symmetry, because if the mean value is very small, the curve will shift to the left on the x-axis, or bigger, it will shift to the right on the x-axis. So you give the location. Then the standard deviation normally describes the spread of the data. So that's why the standard deviation is greater, the distribution will be wider, the curve will be wider, the spread is wider. And when the standard deviation is very small, the spread is smaller, so the curve will shrink in. So we have an example here. They say which curve has the greater mean? Again, from the x-axis, we can see that curve A mean center is 15, curve B is 12. So curve A has the greater mean. The line of symmetry of curve A occurs at s equal to 15, and the line of symmetry of curve B occurs at s equal to 12. Now, which curve has the greater standard deviation? And that will be B, because we can see curve B is widely spread. It's wide. Curve A is shrink, so standard deviation is small. So here we say curve B has the greater standard deviation because curve B is more spread out than curve A. Next example, the height of a fully grown white oak trees are normally distributed. Now the curve represents the distribution. What is the mean height of the fully grown white oak tree? We should also estimate the standard deviation. So based on this, we can see the fully grown, the mean height. This is a normal distribution. So it will be on the center, which is roughly 90. So the normal curve is symmetric about the mean, so the center. Then the standard deviation, we say the inflection point, as we earlier said, is always mean plus one standard deviation. So here we say one standard deviation away from the mean. Now, next thing we should know that a normal distribution with a mean of 0 and also a standard deviation of 1 will give us this curve here. So the mean is 0. To the right, it will be positive values. To the left, it will be negative value. This will be the z values. How we find the z-score is always the value minus the mean divided by the standard deviation. So always again, normal distribution with a mean of 0 and a standard deviation of 1, the z-score is given as following. Now, to find the z-score, as we said, it will be each value of the x minus the mean divided by the standard deviation. So it will be x minus mean over standard deviation. Now, if each data value of a normal distributed random variable x is transformed into a z-score, then the result will be a standard normal distribution, because we can transform each value by subtracting the mean from each value divided by the standard deviation. And that will automatically give us a standard normal distribution. So this is our normal distribution. We have the standard deviation, and also we have the mean, and we are on the x-axis. Now we want to transform the x values to z-score, which means we subtract each x value from the mean and divide by the standard deviation. And that will give us what we call the standard normal distribution. Z gives us S minus mean over standard deviation. So we can use the standard normal table to find the cumulative area under the standard normal curve. And in our textbook, again, we have the standard normal table. So a question given here, the cumulative area is close to 0 for z-score close to z equal to negative 3.49. So area is close to 0 if the z is negative 3.49. We can find this again using the standard normal table in our textbook. And here also we say the cumulative area increases as the z-scores also increase. As we can see, if the z-score is increasing, of course the cumulative area also will be increasing. The arrow shows to the right. And this is the concept of our table also. So the cumulative area for z equal to 0 will be 0.5, half 0.5. So we can see in our table, the z value, the lowest is around negative 3.4547. The highest value is positive 3.4547. Now the cumulative area for z equal to 0 is 0.5. And also the cumulative area is close to 1 for z-score close to z equal to 3.49. And these values are also in the table. So this example of a table, this is just a part of it from our textbook. So we can see the z, this is called again standard normal table in our textbook. We can see the z values on our first column. Then they are corresponding probabilities values inside. So for example, if I'm looking for the z value 0.12, then I will go to 0.1 on the first column. Then I will go to the row of 0.02 because 0.12, 0.02. So which means if I have a z value of 0.12, the corresponding area or the probability will be 0.5478. Now, if I'm looking for z value of 1.2, then I'll go to 1.2 on the column will be 0.00 because I'm looking for 1.2 is same as 1.200. And that will give me 0.8849. Then we keep going on. Again, we will see some examples soon. So the first question said we should find 1.1 in the left-hand column because the goal is to find the cumulative area that corresponds to the z-score of 1.15. So I'll look for 1.1 first. Then I'm looking for 0.05. So I'll go to the 0.05. And that will give me 0.8749. So this is how we read again our standard normal table in our course textbook. We can have a question and they will tell us to find the probability of some value on the distribution, which means the first thing we need to do is find a z-score. When we get a z-score using the formula, we can come to the table, then we can find the corresponding probability of that z-score. Next, they say we should find the cumulative area that corresponds to a z-score of negative 0.24. So negative 0.24, I will go straight to negative 0.2. So negative 0.2, the red arrow is showing the area. Then we look for 0.04. So 0.04 is here. So that will give us 0.4052. So negative 0.24. Go to the z, negative 0.2 across 0.04. So now we know how to read the standard normal table. Now, next is how do we find the areas under the standard normal curve? The first step, we need to sketch the standard normal curve and shade the appropriate area under the curve. Second step, we need to find the area by following the directions for each case shown. So to find the area to the left of Z, we find the area that corresponds to Z in the standard normal table first. First of all, we find the Z value, then we find the area that corresponds to the from the standard normal table. Find the area that corresponds to the Z. Here they say use the table to find the area for the Z-score. Sometimes we may subtract from one or we may do some other. So for example, if I'm looking for my right side, it means if I know from my left to 1.23, I will subtract that value of the area from 1, and that will give me the area of the white side. So for example, from the table, the area to the left of Z 1.23 gives us 0.8907, this area. So if I'm looking for the white area, then it will be 1 minus 0.8907. Because remember, the total area for the normal curve is 1. So that's what use the table to find the area for the Z-score. So here to find the area to the right of the Z, first we use the standard normal table to find the area that corresponds to the Z first. Then we subtract that from 1, and then we get the blue area. Always remember, when you are reading, when you have a Z value and you are reading from the table, the standard normal table, the value that you get, it read from the left, not from the right. So if I have 1.23, I go to the standard normal table. The corresponding area that I get is from left to that 1.23. So if I'm looking from 1 point to the right, then I'll subtract that value from 1. So that's what we have here. From the table, we get 0.8907. If I'm looking at the right side, it will be 1 minus 0.8907, which will give us 0.1093. C, to find the area between two scores. Sometimes we may have a question. We want to find the area between these two scores. So what we did, first of all, we are going to, here they say, find the area corresponding to each Z-score in the standard normal table. Then subtract the smaller area from the larger area. I'm looking for the area here. So I can find the area, the Z-score is given here, so I'll find the area from left up to negative 0.75. Then when I look the table for 1.23, it's also correspond to from the left to 1.23. So now I can subtract the Z area for 1.23 and the area of the Z 0.75, and that will give me the area here. So again, the Z for 1.23 is 0.8907, and then the area to the left is 0.2266. So this means if I want to find the middle, it will be 0.8907 minus 0.226. So now let's see an example. They say we should find the area under the standard normal curve to the left of Z equal to negative 0.99, again to the left. So this means let's do our sketch. We have our z-score negative 0.99. To the left means we are going to share this area. So here we can find the solution. When we go to our standard, again, normal table, we look for negative 0.9, then we go to the across and look for 0.09. And when we do that, we have 0.1611. So we say from the standard normal table, the area is equal to 0.1611. Again, the area is from left, so we don't need to do, there's no need for any subtraction or addition or anything. And so from left, that's correct. Now let's look at the second one. Find the area under the standard normal curve to the right of z equal to 1.06. So first thing, let's sketch it and see. To the right. So what we are going to do first is to go to the standard normal table, find the z for the area for z 1.06. 1.06 will mean from the left to 1.06. So the answer we get, we are going to subtract from 1, and that will give us from the right of 1.06. So let's look the result. From the table, we get 0.8554. Again, to use the table, you go to the first column for z 1.0, then you go to the across column for 0.06, and the intersection of the two will give you 0.8554. So now we need to 1.06 to the right, so we have to subtract 1 minus 0.8554, and that will give us 0.1446. So that will be our solution. Now here they say we should find the area under the standard normal curve between z negative 1.5 and z equal to 1.25. So first thing, let's plot it. Okay, so we have our plot, negative 1.5, 0, 2, 1.25. So the first thing, we can look for the area corresponding to negative 1.50, then the area corresponding to 1.25, then the area corresponding to 1.25 minus the area corresponding to negative 1.5 will give me the area between the two, negative 1.5 to 1.25. So let's see the solution. So first, we went to our table. We were able to find 0.8944 correspond to 1.25. From the table again, when I say table, I mean the standard normal table. We get 0.0668 for negative 1.5. Then we find the difference of the two. 0.8944 minus 0.0668, and the solution will be 0.8276. So we say from the standard normal table, the area is equal to 0.8276. So that will be the conclusion of this section. So in this section, we interpret the graphs of a normal probability distribution. We saw how the mean and also the standard deviation of a distribution have effect, the type of effect on the graph. We also learned how to find the areas under the standard normal curve. This is very important because this will lead us to hypothesis, how to find hypotheses using the z-score value. We may use this table to do that problem. So again, see you in the next lectures, and thank you for your time.